want to welcome each and every one of us to today's class. Today we mark our complete 1 month of the class. This is our 8th class, so I want to say thank you for staying true to this very moment. We shall further continue from where we stop. We stopped at we have really said a lot last week. We talked about nanoparticle. We talked about everything about nanoparticle. We explained what they are. Then we ended at I was explaining the principles that guides modeling of nanoparticle, which I said that the first principle is using a metal, a transition metal for metal complexes. We use transition metal complexes. Then once you identify the metal, the next thing you do is to identify the coordination number of that metal. Please, if your mic is on, help me and switch it off. Clement, your mic is on. So the next thing we do is to identify the coordination number of that metal of your choice. Having identified the coordination number of the metal, you have settled the aspect of the metal. Then for the aspect of the ligand aspect is very, very important to us because there are 1001, there are numerous ligands. So where we have issues is our ability to identify the dentate nature of the ligand. So I took my time last week to explain how you can identify the binding site of a ligand. We'll still touch more. We'll touch other examples, and then I will then explain about the coordination number of the central metal, which is the transition metal, because I did not explain how to identify the coordination number. So today we shall quickly let me share my screen so that we quickly look at the more trend on identifying the dentate nature of a ligand. So let me share my screen so that we will do some exercise right now to see our understanding of last week class. So here I have some drawers. With me. So let me start with hope you have seen my screen. Are you seeing my screen?
No, we are not seeing the screen yet.
Okay, you will see it. Once you see it, just let me know because I've started sharing it.
Okay.
All right. Have you seen it now?
Yeah, we can see it.
All right. So here before
Wait,
me.
it's hanging. Yeah.
Okay. Let's start with losartan. So this is losartan. So look at the losartan. I want people to look at it and tell me what is the dentate nature of losartan. This losartan. What will be the dentate nature? let me bold it more for you. I want to bold it a bit. Let me try to bold it. Okay, we can see it. So look at it and tell me what is the dentate nature of losartan.
It's polydentate now.
Yes, I know it's polydentate. Actually polydentate. Well, if I'm to
It has so many points.
if I am to do this, I will give it bidentate.
Okay.
I will take here as number 1.
Bidentate.
I will take this OH, the hydroxyl first. I will take this hydroxyl and I will take these parts. So these parts and these parts can easily these parts are highly electronegative. They can push out electrons. So I will take these 2 parts.
Which part? You cannot see the part you're pointing. It's not moving.
The 2 blue parts. The 2 parts of blue. Here.
Okay.
This NH.
Okay, the OH.
Yes, the OH.
Mm-hmm.
The OH and the NH.
So that means
so I will likely take these 2 parts.
I can just double for the name.
So, because why we take these 2 parts is when this OH is undergoing bonding, it can give out the hydrogen. So once the hydrogen goes off, that negative charge as a result of the loss of the hydrogen will be available for bonding. The same thing too in this NH. If the N loses the hydrogen, then that very site will be available for bonding. So I will classify losartan as a bidentate ligand. Then let's look at metformin. Let's take a look at metformin. Let me bold metformin. Metformin is a diabetic drug. So look at metformin. Look at metformin. What do you have to say about metformin?
That is poly.
Yes, poly. We have
1, 2, 3, 4.
We have 3. We have 4. Right? So poly. This metformin is tetradentate.
Polydentate.
Yes, it's a polydentate.
Okay, tetra.
Anything from 2 above now is
2 poly.
From 3 above.
Okay, yeah.
So, but just to be specific of what kind of polydentate, we can now call it tetradentate, so that somebody who want to use it, we now know the actual number of the polydentate you are referring to. So it has about 4 available sites that can go into bonding. So you can imagine if you want to use metformin, so you now know how to use it very well. So I will quickly, okay, we are progressing. I just want you, because this is the basic. This is the basis. The other thing is drawing. This is identifying the cavity nature or the binding nature of a ligand is the basis for modeling nanoparticle. Okay, look at bromhexine. What can you say about bromhexine?
Yeah. It's single now.
Yes.
Monodentate.
So it simply means we are now good to go. Yes, we are good to go, because I just have
Your
to.
voice is low. Your voice is low today. We cannot hear you.
Okay, my voice is low. Ah,
Yes.
okay. Okay, let me try increasing my volume, my sound. So sorry.
Can you write it in bracket?
Let me increase my sound.
Which one is this number? Monodent
Ah, my sound
tetradent
is already 100%.
in bracket.
What could be
You don't delete.
It's breaking, oh, it's breaking.
my?
I can't hear you clearly, sir.
I went to increase my sound, but it's already 100%. Okay, don't
So,
worry. You let's see if it's network. But then, can you hear me better?
can you do?
Sir, Pan Black, please mute your mic. I think that's the reason for the breaking.
Then it's DENTATE.
Okay, if your mic is on, just help us and mute it. Can you hear me now? Okay, look at atenolol. Atenolol. What can we say about this atenolol? How many binding sites?
Yes. Yes.
Yes, how many binding sites can we have here? 1, 2, 3, or 4, or 5? How many?
Your screen is not showing anymore.
Okay. No, you will see it. The screen is on. Are you seeing the screen? Are you seeing the screen?
I have not seen it. Not yet.
Okay, but is anyone seeing my screen? Let me reshare the screen then, if that be the case. Let me reshare my screen. Okay. If you can see, just let me know. Eh?
Yeah, I can see it now.
All right. So, can we classify how many is here? Atenolol. We have 1, 2, 3, 4. So I'm seeing 4.
But we can see it, yeah.
Yeah, so I'm seeing 4
It's
for
network.
atenolol. I'm seeing 4. So atenolol has 4 binding sites. 1 here, 2 here, 3.
The screen is off again. The screen is off again.
Could that be, what could be the cause?
It's like you are sharing the screen with another system. I don't know how. Okay, it's up now. It's up now.
Is there any other ones? Who else is not seeing my screen?
You know, I can't see it again. I was seeing it before you went off there.
I can see it now.
Okay, I think that would be network.
The network is there.
That would be network. Okay, it will come up. So I was talking about this atenolol, that it has 4 binding sites. 1 binding sites, number 2 binding sites, 3 binding sites, and then 4 binding sites. So that is for atenolol. So on your own, on your free time, look out for some organic compounds, some ligands, and see. Okay, look at this man. Atorvastatin. How many binding sites has atorvastatin? What can you say? How many can you locate?
Cannot see your screen.
Oh, Oluwa Jesu.
Cannot see this. The screen is not sharing. You can see it now.
You can see it now. It's actually network. You can see it now, right?
We are seeing it now, but you removed it. You have just removed it. Okay, yeah. Can see it now.
Okay, now I think I will know what is the problem. But are you seeing the game draw now? Are you seeing the game draw?
Yes.
Yes, we are seeing it.
Yes, we can see it now.
Okay, thank you. So this is atorvastatin. Is a drug for CVD, cardiovascular disease. For cardiovascular disease. How many sites can you point from here?
3 sites.
3 sites. Okay, let me see.
More than 3. 1, 2, 3, 4.
I can
4.
pick here 1. I can pick here 2. I can pick here 3.
5.
I can pick
Okay.
here 4.
Group.
I can pick
That
here.
means it's 6. 1, 2, 3, 4, 5, 6.
I can pick this place 1. Here 2. Here 3. Then 4. And this place is 5. So I'm seeing 5 for me. But if I'm to design this work, I will pick only 4. I will pick here 1. I will pick here 2, 3, and then 4. So that is for atorvastatin. Alright, you can actually identify as much as possible. I think this will be the last one we identify. Then I will then explain coordination number. So we can start building models. This is a clonazepam. How many can you see here in clonazepam? How many for clonazepam?
3.
Okay, let's see.
I'm seeing 3.
Yeah, I'm seeing 3.
4.
Me, I'm seeing 1. I'm seeing 1 here. I'm seeing 2 here, and then I'm seeing
3.
Although I may not like to count this one.
4.
I would not like to count this one because it was actually part of this range. It got attached from this range. So I may not want to count it, but I will count this one as 1. I will count here as 2. For me, I'm seeing 2 here. 1, 2. Some person may say to count here as 3, but I wouldn't like to pick this one because it's already attached to a benzene ring. So any carbonyl that's attached to a ring, it does not really participate in bonding. Yes. It does not really participate in bonding.
Sir, point blank, please mute your camera. Is the camera? Mute your microphone.
So any carbonyl that is attached to a ring does not usually partake in metal complex bonding. It does not usually because once you break the carbonyl, you are altering the electron cloud density around the carbon where the carbonyl was attached to. So we usually pick carbonyls that are outside the ring for bonding. So on this case, I will pick this amine group 1 and this NO here to be 2. So quickly, I think this is okay for coordination number. You can look out for more for yourself. Look out for more.
Hello, Harry.
Yes.
Hold on. That our negative. That our O minus.
Yes. Yeah.
It cannot bond.
No.
You can't use that.
It will not go for bonding. This O minus is also showing is this place cannot go for bonding. I would like to pick this place because here is actually NO2. This is a nitro group. This is a nitro group. So since that O has minus, we literally will not take it. But this place that has this carbonyl, will go with it because this double bond can easily break. This side you see here can easily break down this side. So this electron here can easily be loosed than the electron here. Maybe that will not permit me to start explaining about bond breaking, like weak bonds and strong bonds, but here has a pi bond. So the pi bond here can easily break than this one here. So that is why we target this carbonyl. So at this point, I'm going to now explain for coordination number, because we just said earlier that what determines the number of the ligand to use is the coordination number of the metal. So the coordination number of the metal is what will now determine how many of that ligand will get bonded to the metal, depending on the cavity nature of the ligand. So what do we mean by coordination number? When we talk about coordination number, I will just try to explain it easier for us using simple terms. Coordination number simply means that active binding site of your metal, the free space of the metal. It means the free space, that available binding site of the metal is the coordination number, because the bond between the metal and the ligand is a coordination bond. That is why we call it coordination chemistry. So the bond that usually exists between the metal and the ligand is a coordinate bond. Basic chemistry we call it codative bond. So now, since the bond is a coordinate bond, that number of free bonding sites, the number of binding site of that ligand, of the metal, is called the coordination number. So if a metal has a coordination number of 4, that means it will need four cavity. Put it that way, it will need 4 cavity. If a metal has a coordination number of 6, it means it has 6 available binding sites. So it will need 6 cavity from your ligand. Now, it then depends on how many cavity does your ligand has. So if I have a metal that has a coordination number of 6 and my ligand has a coordination number of 3. Sorry, my ligand is tridentate and my metal has 6 available space. It means that I will need 2 of that my ligand, two molecules of that my ligand to form a bond, a complete bond with my central metal to fill up the space which is 6. Now, most times you don't usually fill up the total space, but we often advise students to fill up the space, because somebody may ask a question: if I have a ligand that has a dentate of 5, that has 5 cavity for my ligand, and my metal has 6, my metal has 6 binding sites, what am I going to do? My ligand has 5 cavity and the metal has 6 coordination number. So what am I going to do? Because I can't use 2 of the ligand. 2 of the ligand will be supplying 10. What you do is, since the ligand has 5 cavity from how you have identified, and your metal has 6 active sites, if you use one of the ligand, it will not complete the active site of your metal. So what you do is, out of that 5 sites, use only 3. You can use 3 most active sites of the ligand and bind with the metal, because if you use only one of the ligand that has 5 to 6 of the metal, one space will be free for that metal, and that means the bonding is not complete. So what you just need to do is, out of that 5 of the ligand, pick any 3, so that at the end you'll be using 2 atoms of, or 2 molecules of that your ligand. Out of the 5, you just pick 3 sites, so that at the end you'll now be using 2 molecules of the ligand to bond with the metal. So that is the ideology. You must make sure that the metal is complete. But then we have a question to answer, and that question is, what actually determines the coordination number of a metal? If I'm given any metal, how can I know the coordination number of that metal? So let me throw the question to you guys. Does anybody have a likely answer to that question? If I have a metal like copper, we are all chemists. So if you are given copper, how will I know the number of free space binding sites of copper? Do we have any contribution to that question before I wrap it off? I would like you to share your ideas.
Yeah, I don't know. I think it's related to valency, oxidation number.
Okay, you say you don't know, but now you think. Okay, but it's your thought. It's your thought.
The charge.
It's a thought. Yes.
Yes. Yes.
I like that. Okay, any other contribution? Okay. Okay. Let me come in. This coordination number.
Hello, for me. Hello.
Yes. I can hear you. Yeah, go ahead.
Yeah, I think there are so many things that actually will determine. Okay, I think the charge of that metal can determine it. Another thing is the electronegativity of that metal can also determine it. Okay. Not we also regard like structural factors to shape and size, hysteric hindrance, and all those small things like that.
Well, that it bless I don't learn chemistry for your hand though.
Leave the prof, very prof just a scatter.
I don't learn. How much we start our own classes? I'm free on Saturdays.
Well, even me, I
Now you are they learn from all of us. Now Jake and we did and I'm a gangpata for the matter.
You deceiving yourself now.
As well, okay. Now, let me just wrap it off. The charge has a role to play. Actually, the oxidation number has a role to play. But we know that for transition metals, one thing that's common is that they have a variable oxidation number. So they don't have a stable oxidation number.
Yeah.
And
Yeah.
they have lone pairs. But then
Okay.
I'm going to classify them. This how which I'm with a board now. I'll just explain something. But let's see. Let's look at if you look at copper, for instance. Copper has about copper should be 4s1 3d9 normally. Sorry, 4s2 3d9. But due to stability sake, we made copper to become a 4s1 3d10. Am I right? Okay. So now, when you look at the initial 4s2 3d9, you will see that copper, we have one lone pair. Copper will have one lone pair, either from the 3d or the 4s. So that is why copper we assume +1 or +2. That is the most two oxidation states of copper, either +1 or +2. Now, because of that, copper has two coordination number. Remember what I explained about coordination number, the free space, those bonding sites. Because once the orbital is filled up, if the orbital is filled up, it means that there will no more be available space for bonding, because you cannot bond to an orbital that is filled up. It is those free orbitals that are available for bonding. So because copper can assume +1 or +2, copper has a coordination number of 2. Now, the same thing happens to silver. So we can take our time and look at, we can have the configuration of this first series transition element and second series, if possible first, second and third series. Now you will now see the trend. The same thing that happens to copper also goes to silver and gold. So these three commonly have a coordination number of 2. They have a coordination number of 2. Then when you look at nickel is, the shape of nickel is mostly trigonal planar because of the 3 most available free space, because nickel has 3 lone pairs. So I'm trying to relate the oxidation numbers with the coordination number, although it can vary. But I'm giving you the general knowledge, then I will draw conclusion. So nickel assumes mostly 3 transition metal, because the highest charge, the highest state nickel can assume is +3. Nickel can take +1, +2 or +3. Not only nickel, if I can remember, platinum, yes, platinum can also take that same shape. that trigonal. This I will advise you after today. You can go back to study coordination complexes. I will recommend a book for you. I think J.D. Lee is good at. J.D. Lee tried on that area. J.D. Lee concised in organic chemistry by J.D. Lee. I often use it and it was helpful. So nickel and platinum assumes mostly coordination number of 3. Then when you look at manganese has up to +1, +2, +3, +4, +5 and +6 to +7, but it mostly assumes +4, although in most of the ordinary chemical compounds we often see manganese 7, because manganese can take +1, +2 up to +7. Commonly it usually takes +7, commonly, like permanganate 7, and other cases we can cite manganese, but it can take 7 and it can take 4. But because you may not see a ligand who has 7 cavity, and it is not ideal for a ligand who has 7 cavity to even bond to a metal. In fact, the highest number of cavity we allow for bonding from a ligand is 4. The highest we can allow for a ligand is 4. So even if the ligand has 20 cavity, don't use all those 20 for bonding. So the highest we can take is 4. The reason why we are saying this is because we want to mimic what will happen when you also perform the synthesis. We want that if I use my chem draw to model this silver nanoparticle of this ligand, what if I also repeat it in the lab by getting a soluble salt of that metal and probably react it with that particular ligand? If I subject it to characterization, will I expect the same kind of bonding that I have when I predicted with my chem draw? So we have actually studied the nature, the behavior of these metal complexes in a lot of synthesis. So that is why we are now saying that the highest cavity from a ligand you can use in bonding while modeling is 4. Make we no go model something finish come enter lab na different thing wey can happen for lab. But like I told you earlier, that the modeling and the lab work, you should have at least 95% accuracy, and 95% is actually good because we in science we take up 95% accuracy, give room to 5% error. So for manganese, despite that manganese has up to like 7 variable states, we take 4 as the most coordination number. So we take 4. Manganese, cobalt and zinc. Manganese, cobalt and zinc always takes this 4. They take 4. Then another one again is coordination number of 6. Coordination number of 6. In fact, let me say this as upcoming. Generally I always use 2 coordination numbers, 4 or 6 for all metals. 4 or 6 for all metals, because 6 is the most stable, is the most common transition, is the most common coordination number for most metals. Even those ones that is having 2, even those that are having 2 can still take up 6 as their coordination number. They can still take up 6 The only thing that will happen is that the 2d will remain, while the s orbitals will lose one electron. The s orbitals that follows before the d orbital will be the one that will lose the electrons. So most state is 6, but I advise you to always work with 4. So any metal you are using, just take up 4. Take up 4 for any metal you are using, because from my research, from my findings, I've predicted with 6, I've also predicted with 4, but I always see 4 common in most of my finding. And also, not just my finding, one of my boss, Professor I.E. Otokwe, he has been an examiner at Chukwu Metals Ojukwu University for PG students in chemistry department. He has done about he has about 1,500 and more publication on metal complexes. So it was through his ideas that we got this extent. Yes, it was through his ideas, and like I've already told him, by Monday he will be coming up to address us, and he's among those who are signing the certificate. Professor, you can browse his name, Professor Ifeanyi Otukwe. He has done so many work. Most of his work are always on these metal complexes. So most common that we always use is 4. So I advise you to always work with that. Work with 4. For any metal you are using, work with 4. You can work with 4 or work with 6. You have the same result. You can work with 4 or work with 6, but you have the same result. But for a professional advice, I would say work with 4. Work with 4 for a professional advice, because 4 will give us a tetrahedral shape, and the tetrahedral shape is very, very important. When you are characterizing, we look at for tetrahedral shape. If you are doing a nanoparticle, we advise that let the shape of the nanoparticle be either tetrahedral or octahedral. Either tetrahedral or octahedral. So tetrahedral is for coordination number of 4, while octahedral is for coordination number of 6. So once you have a coordination number of 6, your shape will be octahedral. That is for those with a coordination number of 6, and that geometry is very perfect. 6 is very perfect. But as a beginner, I would advise you to be working with 4. And the reason why we work with 4 is to reduce the number of ligands. So that at the end, the complex will not be too heavy. Because if I'm working with 6 and my ligand has 2 cavities, it means I will need about 3 of that ligand. You can imagine forming a complex of one metal with 3 ligands attached to it. Such complex will be too heavy. It will be too heavy, and that is the reason why we often go with 4. For those who want to ask, why do I advise we work with 4? And like I told you, we have noticed that this 4 is very close to 6, and it has been replicated in lab work. So far that we have struck a balance, we can now start modeling and optimizing. So that is what we are going to do now. But then I will ask for a question. So if you have a question, do well to ask me. So small thought, but I don't thought. 9 minutes remaining. Now, wow. So if you have a question, we can do well to ask the question.
Yes, sir.
Yes.
Yes. I want to ask a question.
Yeah.
Yes. There's a work I did.
Yes, sir.
It's not so bulky as machine, but it has 2 line ends. And this 2 leader is coordinated to six, there is a six point, that is the six, what is it called, six coordination number.
Yes, sir.
You understand?
Yes, sir.
Whereby it's coordinated by six this is to the central metal atom.
Yes, sir.
You understand? Sometimes it might have four, as you said.
Yes.
It might have six, depending on the type of ligand you are using.
Yes,
And
sir.
sometimes it's not necessary that it must be up to six ligands.
Yes, sir.
I mean, three ligands rather. Not necessary that it must be up to three. So depending on what your GCMS is telling you, and then from there you can be able to elucidate or try to bring out, and then your FIR is still telling you.
Yes.
From there you
Yes.
are able to know what you are the ratio at which the ligands will form, whether it's 2 to 1,
Yes.
you
Yes.
understand, whether it's 2
To 1.
3
Yes.
to
Yes.
1, or you understand what I mean by 1 to 1. That is
Yes.
one
One
ligand,
ligand,
one
one metal. Yeah.
metal.
Yeah.
Ligands, one metal, or 3 to 1, 3 ligands, one metal,
One metal,
depending
yes.
on what you're telling you.
Yes.
That is the result from GCM
Yes.
and FIR, the coordination. You
Yeah.
see, and you see the fragments, you know what you are up to.
Okay. That's a nice one. That it seems you are working on metal complexes. Hello, sir. Are you working on metal complexes, sir? Oh. Okay. So that is a very nice contribution. Your GCMS will give you idea of the ratio, the proportion of the metal to ligand complex. But at the same time, any structure we are giving in metal complexes, we always say proposed structure, because we are not 100% sure. We will just say proposed structure. Yes. Okay. So we have really dealt with that. I think this week class on this metal complexes has really covered a lot of the area. So if you have a question more, you can ask. But then in the next session, we shall model as much as possible, and then we shall also do the optimization. So at the end, just like I told you, the aim is you can model a particular ligand. You can model up to 10 different metal complexes, test for their effectiveness depending on what you want to use them, maybe as a precursor, for probably as a catalyst, or as a raw material for an industrial process. So you can model as much metal complexes of your choice, and use your in silico tools to check for their activity or properties. Then you can be able to know which one suits you, which one will suit you most in what you are doing. So in the next session, we shall look at everything about the modeling. We will conclude it tonight. It will not be too much. So thank you so much for this first session. Let us